And there are one or two clinical trials that are already, as I understand it, in progress to use this kind of in situ approach of somatic cell gene therapy.
What sort of diseases are people starting to look at?
Well, the ones that I am aware of are, for example, retinopathies. So you can go in and you can edit genes that predispose to certain types of retinopathy.
So that's problems with eyesight at the back of the eye?
Exactly, problems with eyesight. And this is quite a good place to start because the eye is relatively accessible and a great deal is known about the eye. And so this is something which lends itself to this application of CRISPR-Cas9. So this is an example, perhaps the first of many, but it's an example of somatic cell gene therapy combined with CRISPR-Cas9. So somatic cell gene therapy at the moment there are probably over 600 clinical trials ongoing in the US, and it's a technology that's been around for some 25 years or more since the first successful somatic cell gene therapy. So we might see this with CRISPR-Cas9, which is very new, being combined with very well-established clinical technologies. The second non-heritable type of application would be which is a cell therapy, where you take cells from a patient who is affected with a particular genetic condition that predisposes to a disease, and you then edit those cells in vitro in the laboratory, and then you can confirm that you've made the edit that you want to make, and you can put those cells in effect, you can put them then back into the patient because they now have you've now fixed, as it were, the genetic change that predisposed to their condition. And that can happen either by taking cells and directly editing them and putting them back in. And this is largely speculative, although there are one or two ongoing pieces of work. The applications for that are, for example, where you can recover hematopoietic cells from the bone marrow of patients. And then you can potentially edit genes in these blood stem cells and then transplant this bone marrow back into the patient so that now the patient's bone marrow cells have got the repaired version of the cells have got the repaired version of the gene, and the problem is fixed. Another way, perhaps a little bit more futuristic, is where, but it's conceivable, is combining CRISPR-Cas9 with the whole technology of induced pluripotent stem cells. So induced pluripotent stem cells were something that was discovered by a method that was reported by Shinya Yamanaka. He won the Nobel Prize in 2012 for this. And basically what you can do is you can take somatic cells like skin cells, and you can, if you do the right treatment, if you subject them to the right factors, you can cause them to start behaving like embryo-like cells. And from those embryo-like cells, you can ask them to then re-specialize, if you like, into whatever cell you ask them to specialize into. So now we have a system, if we combine this iPS cell technology, where we could, if we have a patient, perhaps a patient with a neurological disease that has a genetic predisposition, we could take skin cells from that patient, because although skin is not the brain, clearly, those cells in many cases would also carry the same mutation. It's just that there's no manifestation of the mutation there because they're not neurons. But we can take skin cells, generate from them iPS cells, embryo-like cells. We could go in with CRISPR-Cas9, so combining the CRISPR-Cas9 here, fix the problem, and then ask these embryo-like cells, these iPS cells, to differentiate to become neurons, which we can do in many cases in many different cell types, and then we can transplant the neurons, which are derived in effect, it's a bit roundabout, but they are derived from the patient back into the patient, but now those neurons have got the fixed genome. So that's another example of non-heritable, because the neuron is not the germline. So that's another example of how CRISPR-Cas9 might be used in non-heritable therapy. And this IPS, not CRISPR-Cas9, but IPS, this kind of IPS approach is being used and has been used in clinical trials, for example, in Japan.
Tony Perry from the University of Bath. And we'll be hearing more from him in next month's podcast, when we take a look at whether CRISPR could be used to genetically engineer humans. And, getting to the heart of the burning questions, I ask whether my friend could hack her genome to grow a tail. You're listening to the Naked Genetics podcast with me, Kat Arney. Still to come, our gene of the month is black and white and very cuddly. But first, back in December, the US National Academies of Sciences and Medicines, the Royal Society in London and the Chinese Academy of Sciences convened a major summit in Washington to discuss the use and implications of using CRISPR for modifying human cells and embryos. The technology to do this is either in place or in progress, but just because we can doesn't mean that we should. Professor Azim Sarani from the Gurdon Institute in Cambridge went along, and I spoke to him during a break at the Progress Educational Trust conference, where he'd been presenting his work on creating egg and sperm cells from somatic cells in the body, such as skin, to find out who went to the Washington summit and what happened there.
Well, there were scientists and there were ethicists, there were lawyers, so it was a mixed group of people. So the scientists were putting their information on, how far the technique has got and what new developments might come.
And presumably what we don't know as well, and what some of the risks are.
There are risks. For example, most of the work suggests that, you don't have particular problems with off-target effects.
This is accidentally cutting things you don't want to cut.
Yeah. I think overall it looks like the incidence of off-target effects is far less than was anticipated. So that's one good thing.
In terms of the technology, we now know that there are researchers who are working on how to take cells from the body, somatic cells like skin cells, and then treat them in certain ways and even potentially turn these into egg and sperm. I mean, that's a whole world, not needing to take an egg and a sperm from a man and a woman and edit them, but actually you could just take someone's skin cells and make a baby and change those genes.
Because, these are children that are not born yet, so you can't talk about informed consent,
It's the kind of the playing God argument.
And then other people say, well, when you have children naturally, you don't ask their permission, You're just passing on your genes.
I didn't want to be born.
Good and bad. You don't go and say, I didn't get permission from the children I gave birth to or something like that, So it's but those are things that did come up at the meeting, and I think that the thing that was surprising to me was that I went there thinking that there'd be a lot of people who would be saying, gene editing, germline gene editing is a red line. We don't cross this. And I found that overall people were much more prepared to debate this, and they didn't say, we should never do it. So the consensus at the end was that we should review this periodically. So they want to see how the science is progressing, what the public views are, whether the public opinion is shifting like it did with some of the other things. So I think, that's a good thing, because I think, we have to see. So I think at the moment the decision is that, people just press on with doing basic research. So if you have, for example, a very good reason why you want to use CRISPR-Cas9 on human embryos, for example, not to implant, but to understand how genes work, how cells are made, and so on, then I think the general consensus is that this should be allowed. I think this could also be the case for cells that give rise to germ cells. That, as I told you, I've already used it in the synthetic germ cells we have made, to understand how genes are working.
But how important is it that this isn't just a decision that the scientists make? Say, OK, we understand the science, we should be the ones who decide how this works.
I think that absolutely not. I don't think the scientists are forcing this issue. I think my reading of the situation is that scientists are excited about the work they're doing, because I think this is a very powerful tool. And so most of the basic researchers see this as an opportunity to gain knowledge. So that's exciting enough for them. They're not necessarily interested in pushing